Oh, okay. So in the previous video, we have seen that how we can write the transfer function on the top level of this 5 transistor OTA, which is called the GM cell. So we have seen what is the influence of the output impedance of GM cell. What means what changes it is creating, how it is making your like DC gain finite, and what other things which is generated by the output impedance. So we have seen this thing on top level, and we have analyzed this GM cell on this top level with the open loop system design. Now we will see this thing in the closed loop system. Okay, so what we will see this top level frequency analysis. Top level, or I should say it is a controlled source structure of this 5 transistor OTA structure. Okay, so top level frequency analysis of GM cell, also called 5 transistor OTA. Okay, also called op amp, single stage op amp. Okay, yeah. So what we have seen the open loop transfer function, where it is taking the input and it is generating a current, and this current is integrated by using this load capacitance. And what we have seen, apart from this load capacitance, this GM cell has some output conductance or output impedance also, which I call R 0, and with this your gain is finite. Okay, what output is coming here. So now next thing what we'll see this thing in closed loop response. Okay, then calculate the poles and zeros and whatever possibly DC gain in the closed loop system. Okay, so when my GM cell, so this is my input that I call C, it is positive terminal, it is negative, and when this is coming in this unity gain closed loop system, what I'm saying here, we are using beta as 1. Other thing also, we can use this non-unity feedback also. It is a unity feedback. So we will analyze one by one and what are the effects. Okay. So with non-unity feedback also we will see it. Non-unity feedback. Again, what I will see, this is my GM cell and this is my input, which is plus minus. Okay. So it is your R1, R2. Here I am getting non-zero beta. Okay, so apart from it, here is a CL where I want to, yeah, integrate this current that is generated. So here, what is your what do you call the feedback? Feedback is nothing but beta times B out. So what is the beta here? Feedback factor is your R2 by R1 plus R2. So this is the non-unity feedback system. Okay. So one thing that is a problem here when we design the op amp, the problem is when we using such feedback network, then there is a possibility that what current generated by this cell should enter into the CL only, so that it can be a proper integrator. But rather, some of the current is going here. So how we can eliminate this problem? We can eliminate this problem by putting a buffer here. Okay, because we were concerned about this output impedance also for the GM cell. What we are seeing, because our expectation was that what is the current is generated by the GM cell, the complete current should go through the CL, so that we can have this better integration, or the perfect, or we can say ideal integration. Okay, but what is happening due to this feedback network, this current is also going through this register ladder, or I'll say register network, register divider network. So there is the division of current. So the current, the amount of the current is generated by CL. Okay, so I should take the okay, yeah, okay. So what I mean to say, whatever the amount of this current generated here should go ideally to this CL. But what is happening? This amount of some amount of the current is going through this register network. So what practically we have seen that even this register was the problem. Even this register was the problem, because what was happening here, the current which is coming out of GM cell ideally should go completely to this capacitive load, which intentionally I want to charge to get a proper integration. Rather, it is going to this output impedance. So this output impedance of GM cell itself is the problem. So what to speak of this external network or load resistance, what we are putting as a feedback network. Okay, but this thing can be this thing can be prevented or can be avoided by using some buffer in between. If we put some buffer here, what can be done? Then there will be no input current to it. What the output voltage will be, what at this node is the same at the output voltage. So we can prevent that current, but we cannot prevent this current to flow inside this resistor R naught, because it is the inherent property of GM cell. Okay, that's why it is creating the problem. This network is not creating any problem. Whatever the load we have here as a resistive load, we can put a buffer and the entire structure is called the op amp. Okay, so what I mean to say, okay, so this resistive network is not a problem. We can put a buffer in between and we can design a structure like this. Okay, so ideally what we want, this is the GM. If I want ideal op amp, not ideal op amp, yeah. So what you can see, if I am saying that there is a only capacitor load, and for the feedback I can put a buffer here with a unity gain, and this buffer is providing me this. It is doing nothing but a voltage division of this output voltage, and it is providing me, sorry, it is a 1. So it is a VF, and VF is going here, it is going here VF. Okay, yeah. So it is generating a output voltage. So what we can see, we can avoid this problem of the current. Now complete current generated by this GM cell is going to this CL and charging it. Okay, so this is the non-unity feedback. I want to concern about it. Now we will see, first we will see the unity feedback and we will draw the transfer function, and after that we will go to the non-unity feedback system. Okay, so how we will write the transfer function for this? This is your V in positive terminal and your negative terminal is like this. This is my CL and I am taking feedback here, which is the unity feedback. Beta equal to 1. This is the output. Okay, so what the current generated? I will write I as a GM times V in minus V out. So this is the current who's charging this CL, and what V out we will get in frequency domain, we will get V out as this I divided by this admittance, which is CLS. Okay, so what this is? It is nothing but GM V in minus V out by CLS. Okay, so what we can see, we can separate this V out on this side. It is nothing but it is 1 plus GM by CLS, GM by CLS V in. So what is the transfer function? V out by V in is GM divided by GM plus CLS. Okay, so this is the transfer function in closed loop fashion. What we can see, it is 1 upon 1 plus CL by GMS. So this is the transfer function. So what the DC gain? DC gain is 1. Okay. And what is the UGB? Your UGB is GM by CL. Again we can say it is same. And we can also calculate for the DC gain, we put the S equal to 0, and for the UGB we will put this magnitude to 1. If someone of you has the confusion how I am getting the UGB means when your gain is unity. Okay, so for that how can I write this thing? I can write 1 plus CL square omega square by GM square equal to 1, and we know that omega at omega UGB is much greater than what we call this GM by, sorry, okay, something we are missing here. Okay, at omega equal to omega GB. So is there any problem? Okay, so DC gain is one. Then after that, okay, 3 dB frequency is your. Okay, we missed something. This is not a UGB. Actually, it is 3 dB frequency. Okay, so it is a 3 dB frequency. So what is the UGB in that case? So it is some wrong interpretation here. Okay, so what we have seen, this is not a UGB. It is a 3 dB frequency. It is a omega 3 dB. GM by CL. Let's take the approximation that omega at omega UGB is much greater than omega 3 dB. Let's take this approximation. But what is happening with that approximation? It is coming as 1 upon CL omega by GM equal to 1. So again we can see omega 3 dB is coming as equal to omega UGB. Okay, which is equal to GM by CL. So okay, at omega GM by CL, the magnitude is not coming to. Okay, so what I can see, the problem, actually the problem coming here is that our DC gain is 1. Okay, so DC gain 1 means it is creating the problem. So what's kind of body plot should be there on this log scale? And you see the DC gain 1 means it is nothing but a 0 dB line. So the magnitude plot is like that. Okay, yeah, this is my magnitude plot omega. So as my DC gain is always 1, so only the omega 3 dB I can say, and what you call it omega UGB, everything is same. Okay, for this particular system where DC gain is coming as 1, because I have taken the unity feedback. Okay, so this was the confusion, we can avoid it. So here we can see this approximation is not valid because our magnitude is only starting at 0 dB. Okay, magnitude is starting at the 0 dB line only. So that way it is happening. Now take the non-unity feedback system. So with the non-unity feedback system, again we will calculate it and we'll directly see some sort of intuition also. Okay, so this is V in. So if there is a CL and after that R1, R2, this is VF is going here. Okay, so with this we think we can see this thing for the closed loop system. What is the V out? V out is nothing but yeah. What the current generated here? The current generated here is highlight. The current generated here is GM V in minus VF. So what is GM V in minus beta V out? Okay. So what is the V out then? V out is this I divided by what is this? I divided by this CLS plus this impedance, which is nothing but 1 upon R1 plus R2. Okay, so from here what we can find? We can see this output by input in the closed loop fashion. We can see here, we will see the output. Okay, output by input, or we will see the transfer function from here. Now, let I come to this structure, which I initially took the unity feedback, but let take this thing in the fashion when we are also having output impedance of GM cell along with this load capacitance. Okay, so again what do you see? Current generated here is I is V in minus V out times GM. And what this current is doing? It is generating the voltage. How it is generating the voltage? It is generating the voltage I divided by CLS plus this 1 upon R naught. Okay, so we will solve this thing and we will get the closed form expression V out by V in. Okay, so these two are relating. This was the external feedback network, and this was nothing but a load of the GM cell. So then we can see exactly this is the fundamental, just what the GM cell is generating as a current and how this current is generating an output voltage. So we'll see what is the closed loop gain, and after that you can plot the body plot and you can see the phase and magnitude things. Okay, so we have seen this thing. Now we will introduce an extra concept, which is the concept of zeros, and we'll see how the zeros are influencing our transfer function and how to calculate it. So now on the top label, let this is my GM cell, and I am having some sort of capacitive feedback, which I call CF, and I want to drive my load. So can you think there is a possibility of zero? How? We'll see. Okay. So what is happening here? So when there are two paths to the zero, so what are the possibilities of calculation of zeros? So when there are two paths, when there are two paths for current from input to, there is zero in the picture. So how will you calculate this thing? So we can see there are two paths from input to output, and when these two paths, the currents are out of phase. So this is a one current that I call I1, and this is the other part to the current I2. Okay. So when there are two paths, then what we can see, if I1 equal to minus I2, then what is the net current generated here? This net current generated here, which was nothing but I1 plus I2 is equal to 0. So what is the output then? Output is 0. So in case of 0 output, we can consider short circuit at output. We can consider short circuit at output, because output is 0 means it is shorted. So what we can see while we are calculating this, so let me call this Vn is this terminal only, and here is feedback, capacitive feedback CF, and it is the load CL. This is the V out. So I can consider this thing as shorted to ground, and then I will calculate this current, and this current should be equal to 0. Okay. Okay. So what is the possibility then? How two paths will be visible? I'll just modify the structure. I little bit modify the structure. What I'll do? Let I call. Okay. This is my, let's say, positive terminal. This is my negative terminal. And if I am taking input, if I am giving input to this negative terminal, and I'm using a capacitive feedback now. Now there are two paths for the current. Okay, this thing you can see now. So because now this capacitor is also between input output, this capacitor is not between input and output. So this thing I have missed here. So you can see here the explanation here, because both the terminals are coming as shorted. Not as shorted, but yeah, at some higher frequency when this cap is shorted, I can consider this node to be 0. So in that sense, we can say the current is not 0. But okay, in this second case, we'll see it. Why I considered this node to be 0? I have considered that at very high frequency, let's say this CF is shorted. Then in that case, this node is shorted and there is no current. Okay, so at high frequency I'll say this CF is not contributing to 0, but at some lower frequency it can contribute to the 0. Okay, but one thing that I considered here, this V out as 0. Okay, so what I'm saying, if V out is 0. Okay, so let's see this second circuit first, then we'll go to the first circuit. Okay, so what is happening here? There are two paths of the current. One is this path, other is this path, and overall current is coming to this way. And if I consider it short, what I mean to say, V out is 0. Then okay, so what is this current? Let I call it I1. Let I call it I2. What is the I1? I1 is nothing but minus GM Okay, and output is shorted. So what is your I2? I2 is my V in CFS. Okay, so what it means, I1 plus I2 equal to 0 means there is a 0, what I call minus GMV in plus V in CFS equal to 0. So from here what we'll see, if we take like V in common, CFS equal to 0. So S equal to GM by CF. So there is a right hand side 0. Right hand side 0. Okay. On this geometric axis plane. So this is the way of calculating 0. So what is the problem with this circuit? Let me see. So what is the problem with this first circuit that we discuss? Okay. So this is my structure and I have given input to positive terminal. Let's say this is my input and I am just considering the negative feedback here with the CL. CL. So I am considering that output is 0, which is nothing but used to calculate this 0. Okay, so this is 0 terminal. Let I call this is some terminal X. So what is this current? I1, and what is this current? I2, and at what value they will be 0, we'll see. And we considered V out is 0 and Vx is some voltage. So what is this I1? I1 is Gm times V in minus Vx. What is I2? I2 is Vxy or Vx times CFS. So if I put I1 equal to I2, sorry, minus I2, or I1 plus I2 equal to 0, then what do you see? Gm V in minus Vx is equal to minus Vx CFS. So let me open it. Minus Gm Vx equal to minus Vx CFS. Okay, so what we can write? GMVN is equal to GM minus CFS Vx. Okay, so this is the equation we are getting here. So now what is the relation between V in and Vx? This is the point. So I think, okay, if we are calculating 0 in this way, then we are stuck at the point where there is a no relation. Okay, one more thing that I can do from this equation, what we are getting the relation between V and Vx. So, what can be there? Again, there is a no possibility. So, it is also giving me CFS equal to 0 means 0 at 0. So, actually, it is not giving me the 0 at the place where we were seeing at GM by CF in this case. Here we are seeing the AMSCS. So why it is happening? Actually, it is happening because there is a path there is no path from V into V out. That's why it is happening like that. But what is the condition for GM calculation? The condition for, sorry, for the 0 calculation is that there should be a direct path relating your input to the output. Okay. So this was the problem in this circuit. That's why I was initially stuck here, and later you can analyze it. Okay. So we have seen here the way of calculating the zero. In general RC circuit, we can also see this thing. If there are two paths for any general circuits, let's say this is my R and this is my C, if they are connecting, and what other sort of things are there, I don't worry. So if I want here output to be 0 for some sort of Vn, then there are two paths for the current. Okay, so what we generally do, we make V out as 0, and what we do, V in minus V out by R plus V in minus V out times CS equal to 0. These are the two currents equal to 0. So what you can see, V out is equal to 0. So what is happening, V in 1 upon R plus CS equal to 0. So what is S? S equal to minus 1 by RC in nothing but a location of 0. So for calculation of 0, sum of two currents should be sum of two currents from input to output should be 0. Okay, it should be 0. So this is the way of calculating 0. In general, we know how to calculate the pole. We have seen also this thing here. So directly from any node, if we can see from here, what is the output impedance, which is nothing but, or the node impedance looking from here is our out. What is the capacitance from here? When we are looking from the outside, it is CL. So directly we can say the pole frequency is 1 upon R not CL. So this is the pole frequency. So actually, I told you how to approach with the current equation, and we directly write the V out by Vn. So which is the transfer function. You can directly calculate the poles and zeros just by looking in two ways. For the zeros, there is a different way of calculation, and for the poles, just look at output impedance, or can say looking in impedance in that node and looking in capacitance in that node. That's it. So we will see this thing further. Okay. So I think this is enough. Here was a little confusion initially, but what we are missing, actually there is a no direct path from input to output. Okay, so this is the input at this node. So there is a no direct path from input to output through the CF. That's why we are missing this 0. But here we have seen the path is there, so 0 can be found here. Okay, and after that we have seen for any in general RC circuit, we can calculate the 0 in this way. So same way, the sum of two currents equal to 0. Okay. So in the further video, we'll see and exactly how to calculate this pole zeros for this 5 transistor OTA structure, which we call the GM cell on top. And internally, we'll see this how these calculations are done, and later we'll write the transfer function for that. So this is enough for this video. Thank you.